So, last class we have seen that if you have given a minimization problem and it is subject to linear equations and objective function is linear and subject to the constraints, the constant also linear, then it is called is a linear programming problem. And we have given a basic idea how to solve that type of problem by considering the two variables, two class of variables. One is basic variables, another is non-basic variables. Then non-basic variables which are the we will assign as a non-basic variable, that variables values we are assigned to a 0, and in turn we get a basic variables values. Then we shift one of the non-basic variable values we convert into a basic variables, and one of the basic variables is converted into a non-basic variables, and which non-basic variable, which basic variable will be converted into a non-basic variable, and non-basic variable which one will convert it into a basic variable, that we have discussed yesterday. Let us see that what we can do with the what is called in algebraic approach, matrix and vector form. So, numerical method of solving the linear programming is known as the simplex method. So, let us call the algebraic, we have just discussed the algebraic approach to solve linear programming problem. This method is an algebraic approach, the algebraic approach or numerical method, that way we will solve the linear programming problem is known as the simplex method. So, let us call our minimization problem minimize f of x, x dimension is n cross 1 and decision variables are there, and that we have written into a C transpose x n cross 1. Immediately you know what is the dimension of the f is a scalar function, objective function is a scalar we have defined. So, this we partition into two parts, this C transpose matrix we partition into two parts, C V transpose partition C D transpose. That C B transpose will be associated with the basic variables x b and x n, non basic variables, which is denoted by n. The dimension of this x b vector is m, and this dimension from here to here, this dimension is n minus m. So, and subject to what? This objective function is linear function and subject to our constraint, and that constraint is a set of linear equation in terms of x variables, and x is a n components. So, we have a x which is a n components are there is equal to b, and we have a m number of linear equations. So, this dimension automatically it will be m cross n. So, this also we have partitioned accordingly our what is called basic variable associated with the basic variable and non basic variable. The matrix A is partitioned into two parts, B partition D, then it is a x b, then x n is equal to B cross 1, and this dimension immediately you see this is m rows and this is B has m rows, and this as a you can say this as a n minus m rows. So, this A is partition B into B and D. So, and we are then x, all components of x is greater than equal to 0. In other words, we can write this x is partitioned into two parts, x b which is a basic variable that values are non-zero, and x n which is a non-basic variable, these values are also greater than equal to, this value is equal to 0. This is n is equal to 0, this. So, this we have partition that x values are greater than 0, then we have partition x b and x n. So, if we consider that our non-basic variable are x, last n minus m variables are non-basic variable, that values will be assigned to a 0. So, this dimension is n minus m into 1. Okay. So, from this is, let us call this is a set of equation which is equation number of 1 this. So, if we consider the non-basic variables x n, x capital N is equal to 0, then from 1 we can write it, from 1 we can write it, see, b into x b plus d into x n is equal to b, but this value is, we have considered non-basic variable which is equal to 0. So, we will get a basic solution, and that basic solution must be a feasible solution. Feasible solution means x is greater than equal to 0 and we have to, all constant must be satisfied, and this naturally it will be satisfying this one. So, our therefore, our x b is equal to b inverse into small b. So, this is our basic variables, we got it. So, our basic variable solution now, so our basic variable solution are the basic variables, basic feasible solution x is what, x b, and this value you know at this moment, and this is x b is b transpose b inverse b, and this x n which is equal to 0, these non-basic variables. So, this is, these values are greater than equal to 0, this one. So, so let us assign this equation number is what we got it, this x b value, this is a 2 and this is equal to, or this equation you give it 2, forget about this. This equation number you will recall this equation once again. So, and this equation is equation number 3. So, now we can find out that whether there is a, next question is what is the corresponding cost function value. F of x, because we have assigned out of n variables, if you see we have assigned n minus 1 m variables is 0 and remaining m variables values we can get it by taking the inversion of v inverse v, and that is called basic variables. So, basic feasible solution, that what we got it, basic feasible solution is this one. Then corresponding function value we can find out. What is this function value? If you see the our objective function expression, this is C b transpose into x b plus C d transpose into x n. So, x n value is 0 and this values we got it is C b transpose, and x b value we got it, you see b inverse small b, say that value is 0, z 0 say, and that is equation number 4. So, basic step of simplex method is there. We are now having a feasible solution x. From there, that vertex, if you move to another point in a feasible region, then we want to see whether that point will reduce the function value from the present vertex or not. If it is reduced, then we will accept it. Agree? So, this is our basic idea of what is called the simplex method. What is the feasible solution is there now, basic feasible solution, we will move to another adjacent feasible point or feasible vertex, and at that vertex if the function value is less than the previous point, previous and adjacent point function value, then we will accept that one. Agree? So, let us see how logically we will proceed that one. So, this basic step of simplex method is to move to another adjacent feasible point, so that the function value, so that the function value means cost function value is reduced in such movement, that is the basic idea of simplex method. So, let us call we have a set of linear equations are there, and this is the vertex of this one, and these are the all feasible region is inside this polygon, and this is the vertex. Let us call this vertex is x u, or you can write y, this is y, u, b, w, z, this is y. So, if we move the adjacent vertex, I can move to adjacent vertex is here or at this point. I know the function value at this point y point. If the adjacent point, if I move it, agree, if the function value is less than the value of the function at point y, then we will accept that feasible solution of this one of the feasible, but that feasible solution may not be what is called minimum. So, you have to look that any one of these vertices will give you the minimum value of these functions. Agree? So, this is not the adjacent, to y. Adjacent to y is u is adjacent to y. This is adjacent to y z, but w is not adjacent to y. So, you will move immediate adjacent to our present feasible solution whatever we got it. So, let us say with this one that what happens, next question will be what happens if the one of the non basic variable x n, all non basic variable we have assigned 0. If we change one of the non basic variable to a basic variable, means non basic variable all variables value is 0. If one of the non basic variable we make it non-zero, agree, then what will be the function value will increase. Next question, which non basic variable will increase out of n minus m variables, which non basic variables will increase it. So, this is the question. So, if we increase that, if we just move that point, naturally function value will change, increase, because function value will increase, that which variable will move it, depending on this one function value may increase, may decrease also. So, you have to take the judicial decision that which variable of non basic variable will increase its value. So, now question is here, what happens if 0 component of x n, x capital N, it has a n minus 1 component, all components are zeros, increases to some value so what happens if 0 component of the increases to some value? The non-zero component of x, you see the non-zero component of x b, that basic variables values are non-zero. The non-zero component of b must drop by B transpose B inverse D x n to maintain equality constraint, equation 2. So, equation 2 you see this one. So, if because you see now this D is a matrix, now all elements of x is 0. Out of all these things, one element if I increase it, increase it and corresponding column, that corresponding column of D which multiplied by that element of that is x n, agree, this corresponding element if we multiply by this one, that value will not be equal to B until unless there is a drop in these components, agree. So, we can write it now from this equation, that is what we have written it, I minus B I not minus I B inverse D x of B minus B D inverse x n and x n must be equal to the right hand side B inverse B. See here what I did it, both side I multiplied by B inverse, agree. So, x B, now it is writing B inverse D x n, agree, and right hand side is B inverse B. Now, I am telling you out of n minus m element, one of the element is non-zero. So, naturally the corresponding element multiplied by that corresponding column of that one, this product, agree, this vectors will is added with this one. Previously it was 0, its contribution was 0, now it is added with this one. So, in order to satisfy right hand side B, there must be some component of this one, it has to be drop out. So, this is now coming into the picture. So, this I can write it now, if you see this one, that x n into B is, if you multiply x b into this, then x b inverse what is called B inverse D x n, it will be cancelled, and ultimately it is x b is equal to B inverse capital B inverse B. So, this part is increasing and from the x b this part is drop out. So, this is the condition is that if you change one of the variables of x n, if you change it, there must be a drop in from x b, some component of x b must be drop out. So, this. So, now total change, or that you can say that changes the cost function is, see this corpus, what is our C b transpose into x b, what is x b? X b now this whole one, x b minus B D inverse x n plus C D transpose, this is our performing objective function C D transpose into x n, this one. So, if I one of the element of x n, that out of n minus, if one of the element, if we change it, there must be from x n some x b vector, some has to be drop out. So, that this equation is satisfied, this is the thing. So, if you readjust this one, I can write that C transpose B and x b you can write it, this x b is nothing but a B inverse small b plus this term minus this into this, C transpose x n minus C B transpose B D inverse x n, this is x n, agree, this is x n. So, now this is C suffix, this is C suffix b, C suffix b. So, this is term C suffix b, B inverse b. This is a our previous point objective function value. What is the previous function value? If you change x n to some other value, then this changes are coming, C D transpose minus C B transpose B D inverse whole x n. Okay. I think here I have written C B. So, this is not a C B inverse D, B inverse D. So, this is, if you manipulate this one, C B D inverse this, agree, B inverse D, B D inverse, not D inverse, B inverse, just a minute. So, what we got it is that one, this is B inverse, sorry, here you just make it correction, because this is B inverse, this is B inverse, this is not inverse, drop, this is B inverse, this is not drop out, agree. When you have just x b value is this one, then this is your B inverse, this is not there, this is B inverse, this is not there, agree. This is I mistake here, B inverse. So, now you see this term, if you see this term f of x is coming, f of x is coming z 0, the original point objective function value plus that your C D transpose minus C B transpose B inverse D into x n, and let us call, I consider this is a R D, this is a row vector, this is a row vector of dimension n minus m into 1, this, because this dimension is n minus 1, n minus m in n row, this is a column vector, this is row vector. So, I write it a R D transpose into x n. Now, see this one, this function value, if I change the non basic variable value from 0, all values are 0, from there if I change it some value, some of the element, if I change its value, then the total value of this one is coming in the next point is z 0 plus R D transpose into x, and this quantity is scalar. Now, it depends on whether the function value will decrease or increase, it depends on the row vector elements of row vector of R D transpose, because one element we have to increase because r x n the variable is greater than or equal to 0, you have to increase it. So, this function value will decrease when if corresponding element of x n corresponding element in r if it is negative, because x n is x n that which element you have considered is a positive, that corresponding element in R D transpose must be negative. Then there is a possibility of reducing the function value. That means, so we have a this you can write it, the cost value you can write the cost value goes up and down, up or down, that depends on the value of, depends on the elements of, or you can say on the sign of the vector that means R D transpose is equal to C D transpose minus C B transpose B inverse D, this one. Now, let us call, if this is a row vector, if you consider the all elements of this row vector, all elements of the row vector R D transpose all are positive, agree, and the x n, how many elements are there in of x n vector non basic variable? There are n minus m elements. Out of this one element, let us call, I want to change its value from 0 to its value, I want to increase it, agree. Then this function, product of this function will be a positive, because all elements of this, if I consider positive, then this product will be positive. So, objective function value is increasing. So, we are now away from the our goal. Our goal is minimizing the objective functions, this one. So, if you think in other way, if R D transpose is less than equal to 0, or the elements, at least one elements of R D transpose is one is negative, and corresponding element of x n, element of x n is positive, then product of this one will be a negative one. So, there is a scope of finding the value of f x is finding the value of f x to be reduced, agree, or to reduce the function of value of f x if you move that point. So, whole thing whether function value will increase or decrease, that depends on the R D. So, in short, now we can write it that if R D transpose is greater than equal to 0, that means all elements of R D is greater than equal to 0, then R D transpose x n is greater than equal to 0. Since x n is greater than 0, we have considered one, at least one of the element is non-zero, that. So, the best decision is to keep x n is equal to 0. So, x n is equal to, suppose R D is all elements of this, and if you consider all elements 0, then x you want to increase it, then this product will be greater than 0. That means, function value is increasing. Then it is better whatever the point you are earlier at that point you keep it as an optimal point of this feasible solution, agree. So, another choice is that as all the elements of this, if at least one element, one component of R D transpose is negative, at least one out of how many elements are there? N minus 1 elements of R D. Out of this, at least one element is negative, then corresponding x n element, which is multiplied by x n element, corresponding element, that element, if you change from 0 to non-basic variable to basic variable to 0 to increase this value, the function value will decrease. That is why, if at least one component of R D is negative, then the cost function, cost value can be reduced by increasing the corresponding component of x n, by increasing the corresponding component on x n. Okay. So, now if you find that there is the R D, that row vector R D transpose row vector, if there is a more than one component having a negative sign of that R D transpose, that row vector element, more than one element is having a negative sign, then which corresponding variable of that R D you will consider as a basic variable. The most negative negative sign of that numerical values we will consider as a basic variable, because that will give you the reduction of the function value much than the other negative value of in R D x R D transpose. So, after R D is computed, after R D is computed, the entering basic variable, let us call x I, is determined by the largest negative coefficient of R D transpose, and it allows that component x I to increase from 0. Next is we have increased this one. So, just now you mentioned it here, if you recollect. So, one of the non-basic variable is now chosen as a basic variable. Now, one of the basic variable, now we have to select as a non-basic variable. Out of m basic variable, which basic variable we will consider as a non-basic variable, that we have to select it. Next is how now which component of basic variables x b will treat as living basic variable. That means, that basic variable is living and entering as a non-basic variable, which basic variable we will consider. That is the next question, entering as a this which basic variable leaving and entering as a non basic variable. So, now recall this our basic expression, that is I B inverse D x b x n is equal to B inverse B. That is our basic expression. That is our what is called equality constants are there. We have written, if you recollect B, we have, if you recollect this one, we have written B partition D, then we have a basic variables x b, then we have a non basic variable x n is equal to B. So, both side I inverse, this is a square matrix, this is a square matrix, both side I took the inverse all this. So, it will come this way. Now, you see I have this, if you consider the ith component of x n is non-zero, remaining element is, how many components are there here, x n, n minus m. Out of this, ith component of x n is non-zero, other is 0. So, if you multiply it by B inverse D with x n, agree, if you multiply it by this B x, so first component of this one x n will multiply it by first component of B inverse D, plus second component of x n will be multiplied by second component of B inverse D, and so on. So, I have considered the ith component of what is called x n will be multiplied by ith component of B inverse D, that component will be multiplied, that will be non-zero, other remaining element will be, column will be 0. So, I can write it now. Let us call ith component of B inverse D is equal to this small b into, I am considering ith component of this one multiplied by x I, agree, this is this, then what is this component will be there here, x b plus is equal to B inverse B. So, this dimension if you see, it is a m cross 1 and this dimension is your m cross 1, this is 1 cross 1 by ith column and this one. So, this is, you can write it, this V is what? V is the ith component, ith column, not component, ith column of B inverse D, this. So, this is equation number, we have come up to equation number 5, 6, let us go up to 5, this is 6, this is the equation number 6. Now, we can write it, see this one. When this component will be 0, when you see this ith component of ith column of B inverse D, I multiplied by x I, because x I is non-zero, corresponding column of B inverse D is multiplied, and this is B inverse, capital B inverse B. When this component that is, it has a m components there, out of m components, components, you say which components, because this x b components will be 0 when this equal to this, when this equal to this, and how many components of this you have B, you have a m components are there. So, it will be a this B 1 x I, B inverse of B, if this is equal to same, x b will 0. Now, out of all this, in which element of x b, that basic variable, will force it to make it 0? Agree? That is our next question. So, let kth component of x b. So, how many components are there here? M component. Out of this mth kth component of x b will drop to 0. Agree? Then from equation 6, from 6 what you can write it? The kth component of this is assigned 0. So, we will write it V bracket x I V inverse of V. Agree? I told you here, I have just mentioned it, kth component of this as a m variables are there. Out of m, I am just considering kth component of x b is forcing to the 0. So, if it is a forces to 0, then this equal to this, and that is also you have to consider kth component of b, and here also you have to consider kth component of v inverse of small b. So, that is why I am writing here the kth component and this is also kth component. That this vector is you are having a m cross 1 column vector of m elements. Out of this, that mth component I make it the x b mth component I am forces to the 0. That means, in other words, that basic variable is entering as a non basic variable, that kth component x b I am assigning to 0. So, this equation must satisfy it. So, then I can write it x I is equal to is kth component of B inverse of B divided by kth component of V, and this must be greater than equal to 0. That is, let us call equation number, we have given 6, that is 7. This is why it is greater than equal to 0, because denominator part cannot be negative. Why it is greater than 0? When you will compute the basic variables expression from here, you see, when you will compute the basic variable expression here, this the kth component of this one, I can write this kth component of this one minus, if you take that side, minus kth component of V, agree, into x I, Since x I value is greater than 0, that minus V I and x I, this will be 0, provided V, that this coefficient kth component of this one is positive. If kth component of this one is positive, if you take that side, it is a scalar quantity, kth component of V is scalar quantity. If it is a positive, if you take that side, it will be negative, agree, and then k x I is your positive. So, this positive quantity minus whatever this quantity, this minus of this quantity, it has a chance of making this is 0, and if it is a negative this one, agree, if it is a negative of if the kth component is negative, it goes to the next right hand side as a positive, multiplied by positive quantity, because x I is now is the basic variables. So, this added with the positive quantity, agree. So, this value will increase, we will not be able to force it to 0, that one. So, that is why this is greater than 0, this we have to consider. The smallest. So, we have a such type of things, there may be possibility we have a such type of xi choice, m choices there. Out of this, the smallest of this ratio will be treated as LBP, living basic variable. Say xj. So, xj, say xj. So, our new corner point or new vertex will be what? At the new vertex, new feasible solution you can say, or new vertex or new corner point xi has become positive, and as j has become 0. Agree with this choice. So, keeping all these thing in mind, we will see now how to solve these problems, how to solve that our linear programming problem using the simplex algebraic approach, simplex method using algebraic approach. So, we will take our earlier problems what we have discussed, that minimize f of x is equal to x 1 x 2 plus 5 x 3 minus x 4, and subject to x 1 plus 2 x 3 plus 2 x 4 is equal to 6, and x 2 plus x 3 minus 2 x 4 is equal to 3. So, this is, and your x I is greater than or equal to 0, I is 1, 2, 3, 4. So, if you recollect that last class we have just considered that problems, this problem where x I, x 2, x 3, x 4 is greater than or equal to 0, that is we have considered last class, that one. Agree? And we have seen that which component we have to consider in non basic variable and basic variable to reduce the function value from previous point to new point, the function value must reduced, this one. Now, we will see that this algebraic approach how can it be applied to solve these problems. So, first you identify the matrices, A matrices and our other matrices. So, first is initialize. So, see our A matrix is that one, quickly you can write it 1 0 2 2, that is 0 1 1 minus 2, and you can think of it, this is the x 1 coefficient, x 2, x 3, and this column when you think of it, x 1 into 1, x 2 into 0, x 3 into 2, x 4 into 2 is equal to B. B matrix is your B vector is 6 3. Similarly, you can think x 1 into 0, x 2 into 1, x 3 into 1, this one plus x 4 into twice x is equal to 3, this. Now, our which one is our first iteration, which one is our basic variables? Basic variable we will consider this one, agree, which are in the canonical form. These are canonical form. X 1 is involved in equation 1, x 2 is involved only equation 2, So, these two we can think of as the basic variables, that are non-basic variables are x 3 and x 4. So, we are now partition x 3 our x 1, x 2 our basic variables, x 3, x 4 are our non-basic variables. So, this is written as x b, so x n, agree. And what is our C? C transpose matrix, you see 1 1 this. So, our C matrix is yours, if you see here 1 1 5 minus 1, and this corresponding to x 1 and this corresponding to x 2, this corresponding to x 3, x 4, this you can think of it, x 1 into 1 plus x 2 into 1, x 3 into 5, this one, x 4 into minus 1 is equal to our objective functions or cost function. So, if you see the C B, this matrix corresponding to the basic variables, and it is x 1 x 2 are the basic variables, and this corresponding to our non-basic variable x 3. So, this we have partitioned like this way, and you know our C is what and B is what. I can just partition now, I can just partition like this way. Our B is your 1 0 0 1 B, D is your 2 1 2 minus 1, agree. This is our D. Similarly, we can say that our CB transpose is equal to 1 1 and CD transpose is equal to 5 minus 1. So, this we have envisioned. Now, second step is checking the stopping criteria, Agree? What is the stopping criteria? How to check it? That you have to find out your RD what is called RD transpose, the row vector. This is a stopping criteria to see. So, let us say our B D multiplied by x b and x n. This value is non-basic variable, we have considered 0 is equal to 6 3, this one. So, our basic variables solution is x b is equal to 6 3. So, if you get any component of x b is negative, this indicates that solution is not feasible, because our problem was x is greater than equal to 0, this one. So, now let us say that our initial, so we can write it now, initial vertex or corner or initial feasible solution, we got it, vertex or corner is what? X 1 is, we got it, that is x, we got it 6, x 2 is 3, x 3 0, this we got it. Now, what is the cost function value? Cost function value is C transpose into x, which is equal to C B transpose x C D x b, C D transpose plus, this is plus C D transpose x n, agree. So, this value is 0 and this value C B transpose 0, this into 6, 1 into 6 plus 1 is C B value is, C B transpose is 1 1 and this is C B is 6 3. So, if you do this one, it is 9. So, our objective function value is at this point is 9. Now, we have to say whether we can, if we move one of the non-basic variable to basic variable and basic variable to one of the basic variable to non-basic variable, whether the function value can be reduced or not. So, now compute to know this one or to show this one, compute R d transpose. If you recollect this one, we have derived R d transpose C d transpose minus C b transpose B inverse D. So, this equal to C d, you know, nothing but a 5 minus 1 minus C b, you know it, C b is 1 1, B transpose B I know is identity matrix, agree. So, D is your 2 1 2 minus 2, see this is our D. So, if you compute that one, ultimately you will get it here 2 minus 1 this. Now, you see R d measures that this coefficient, because R d multiplied by what is this x n. If you think of it is a multiplied by x n means x 3 x 4. So, it is multiplied by x 3 x 4 R d. So, there is a minus sign coefficient, reduction coefficient. So, if you change x 4 value from 0 to some positive value, there is a possibility of reduction in cost function below, and x 3 is 0, I have not changed it. So, there is a possibility if you do this x 4 value, you change it to non 0 values, that means some increasing value. So, x 4 will go act as a non basic variable and x 3 will remain as a basic variable. So, I will stop it here today. Next class I will continue the remaining part of this problem.